Hello, this is 4.4, a closer look at testing. Now, before I start 4.4, I need to remind you of two notes from 4.3. The first one, the relationship between p-value and alpha determined whether I reject the null or not. Remember, when p-value was less than alpha, we rejected the null. And when p-value was larger or equal to alpha, we didn't. The second note is that rejecting the null determined the significance of my results. When we rejected the null, we said that our results were significant. But when we didn't, or we failed to reject the null, our results were called inconclusive. Now, if you remember these two notes, perfect. If not, please write them down because you'll need them for this section. The hypothesis testing were an amazing tool that we use and we still use because they basically determine whether my results is significant or not. However, like anything else, there is always some portion of error in these tests. Now, what are the situations? The situations are either the null is false and we reject it, and that's a good thing, or the null is true and we don't reject it. That's again a good thing. Type 1 error happens when you reject a true null. There isn't there isn't any evidence, and you rejected the null. This is type 1 error. Type 2 error happens when you fail to reject a false null. There is evidence that something's happening, but you fail to see it. Think of it from a medical point of view. Type 1 error is what we call false positive. We're finding evidence when there shouldn't be evidence. The null is true, there isn't evidence, and yet we're rejecting that and saying, no, there is. So this is what we call a false positive. Type 2 error is what we call a false negative. There is evidence, but we don't see it. Look at these two images. Type 1 error is rejecting the null case. This is a man. A man cannot be pregnant, and yet you're saying there is some evidence. You're rejecting the null and saying there is evidence. Type 2 error, this woman is pregnant, there is evidence, and yet you're failing to see it. Also think of illness. Somebody is sick, and they take the test, and the test showed negative. This is what we call again a negative false. This is type 2 error. Let's imagine another case. Someone is not sick, healthy. They take the test, and it shows evidence when they are not sick. This is type 1 error. Let's look at it from a different perspective, from the law perspective. A person is innocent until proven guilty. The null case is that the person is innocent. There is no evidence that this person committed any crime until proven guilty. So guilty is the other case that this person has actually committed the crime. Evidence must be beyond the shadow of doubt. Evidence in terms of statistic were determined by the p-value. And we said that the p-value needs to be less than alpha. So alpha is the shadow of doubts. The types of mistake that could happen here, type 1 error and type 2 error. Convicting an innocent or releasing a guilty. Now, convicting an innocent would be type 1 error, showing evidence even though this person did not commit a crime. Type 2 error would be releasing a guilty. There is evidence that this person has committed crime, and yet we are failing to see it. Example 1. A consumer protection agency is testing a sample of cans of tomato soup. If they find evidence that the average level of the chemical BPA in tomato soup from this company is greater than 100 parts per billion, they will recall all the soup and sue the company. State the null and the alternative hypothesis. So first we need to determine what population parameter we have. In this case, we have a single average. So when I write the null hypothesis, I say H0 is mu equal to 100. Remember, the null always includes the equal sign. The alternative, on the other hand, will follow the wording of the question. In this case, we are trying to show evidence if the chemical substance average is greater than 100. So the alternative would be mu greater than 100. Part B. What does type 1 error mean in this situation? Type 1 error means that the company's mean, that the company's average, is within normal bounds of 100. But the sample obtained happens to show that the mean is too high. Basically, what we're saying is that the population of the tomato soup contains this chemical substance within the bounds of 100. So it is a healthy population. However, the sample that we are obtaining showing false positive or showing wrong values that the chemical substance is higher than 100. So obviously the consequences in this case, they will recall all the soup and sue the company. So these are negative financial and legal consequences. What does a type 2 error mean in this situation? Type 2 error means that the company's mean is too high, but the sample obtained doesn't give sufficient evidence to show that. So the general population of the tomato soup contains more than it should of that chemical substance. And yet, the sample that we took didn't show any evidence of that. So the consequences in this case is that they will not recall the soup. Basically, they will send it to the consumers, and this might cause some health problems. So which is more serious, type 1 or type 2? In most cases, both types are serious. You either have financial, legal, or health issues, and you really want to avoid all of these issues. In this situation, it is better to repeat the experiment and have a larger sample size, because whenever you increase the sample size, you are producing more normal values. So we always wish to avoid both types of errors. In practice, however, we have to accept some trade-off between them. If we make it very difficult to reject the null, we could reduce the chances of making a type 1 error. Remember, type 1 error was rejecting a true null. So if we make it harder to reject the null, we will reduce type 1 error. However, if we don't reject that much, then we are increasing the chances of making type 2 error. On the other hand, if we are making it easier to reject the null, so we're rejecting all the time, then we are decreasing the chances of making type 2 error. So again, let's remember, type 2 error was not rejecting. So to reduce that, we will make it easier to reject. However, if we are rejecting more than we should be, we are making more type 1 error. So this balance is set by how easy or hard to reject the null. Remember, before we started, we said that you need to remember for this section that rejecting the null was determined by alpha, by the significance level. Let's see more examples. Look at the two graphs up there. So this is a normal randomization dot plot. Decrease the chance of making type 1 error. Type 1 is rejecting too much. We will make it hard for us to reject the null. Basically, we will use smaller significance level. And this is very important. You really need to write this down. So if you make it alpha small, then the cases that are extreme becomes the chances of having extreme values is less. So you'll make it basically harder for yourself to reject the null. On the other hand, to decrease the chance of making type 2 error, we make it easier to reject the null. So if this is the normal situation, to make it easier, we will increase alpha. This way we will have more extreme values and it'll be easier for us to reject. Remember, type 2 error was not rejecting enough. So we need to make it easier. So write this down. To decrease the chance of making type 1 error, use a smaller alpha. To decrease the chances of making type 2 error, use a large alpha. So which alpha is it? Should we make alpha big? Should we make alpha small? What do we do? It all depends on the consequences. If the consequences of type 1 error are severe, then we use small alpha. Let's think of that. Let's say you want to introduce a new drug that has serious side effects. Then you only want to administer this drug to the people who need it. You want to avoid the false positive. So if you want to reduce the type 1 error, you will use a small alpha. On the other hand, if the consequences of type 2 error are severe, then we will use a relatively large alpha. Again, let's think of another situation. Let's say you want to introduce a test that would detect diseases that are easy to treat. Then you want to make this test effective most of the time or all of the time. Basically, you want to avoid the false negative. In this case, you will use a relatively large alpha. So it's really up to the consequences. Alpha in general could be any percent. The common values are 5%, 10%, and 1%. So if you want to reduce type 1 error, you want to use a small alpha. So you might end up using 1%. And if you want to reduce type 2 error, you will use a relatively large alpha. So you might end up using 10%. It really depends on what are you testing and what consequences are you looking for. The next note, you really want to write it down. If the null hypothesis is true, alpha is the probability of making type 1 error. Now let's study this case. We said earlier in 4.3 that determining whether to reject the null or not is based on alpha. So if the null is false and we rejected it, then we are in the clear. We are fine. However, if the null is true and we rejected it, then we will be making type 1 error. So the chances of making type 1 error will be exactly equal to alpha. Meaning, if alpha equals to 5%, then the probability or the chances of making type 1 error will be 5% of the time. Same thing, if alpha is 1%, then the probability of making type 1 error will be 1%. Another part of this section is called multiple testing. Now, in most cases in our Math 117, the ones that we've done in 4.1, 4.2, and 4.3, were all about cases with singular hypothesis tests. And we would perform that test with that single alpha, and we will produce the p-value and so on. In real life situation, they would use multiple testing at once. Probably they would be testing thousands of hypothesis tests using the same alpha. And what happens is they will end up rejecting something that they shouldn't reject. So basically, what you need to remember, multiple testing produces more type 1 error than we should have. Another problem is the publication bias. Now, what does that mean? Publication bias refers to the fact that usually only the significant results get published, and no one knows about the insignificant results. Now, keep in mind, most of the time we are rejecting the false null, and that's okay. However, we just saw that there are times when we reject a true null. Basically, we are showing significant evidence even though we shouldn't be. So if every significant result get published, we might be publishing something that is not true. So let's see an example and then we'll talk about how we can avoid these two problems. So look at example 2. In this exercise, we are conducting many hypothesis tests to test a claim. Assume the null hypothesis is true. So in this case, we know that the null hypothesis is true. Basically, we shouldn't reject this null hypothesis. If 120 tests are conducted using significance level of 5%, approximately how many of the tests will incorrectly find significance? So out of the 120 tests, how many of them will be false positive? So we will use the note that I asked you to write. Alpha is the probability of making type 1 error, basically showing significance when we shouldn't. Alpha in this case is 5%, so the probability will be 5%. So 5% of the 120 will be 6. And this means out of the 120 tests, we will have 6 of them will show us a false positive. So let's look at the problems that we have or we will face. The first problem is the fact that we will make errors. We have type 1, we have type 2 errors. The other problem is that because of financial reasons, we will end up, or most of the time, we will do multiple testing. And we might end up publishing something that is significant even though it's not. So how can we avoid these problems? The first way we can do this is to actually look further. Look at the results we are seeing. Think, how accurate are they? Who are they benefiting? Think of these tests. Are they significant enough or not? Do they make sense or not? The second thing, and this is the best thing you can do, is replicate the results. A replication method, basically, you would ask another researcher or another company to redo testing on the same hypothesis. So if other companies did the same testing and they had the same results, then your results will gain credibility. However, if the other companies did the same test and produced different results, you will lose credibility. So replication is really good because it basically emphasizes the credibility of these results. Okay, let's see some examples before we move to the next point. So here are some review questions. How can we reduce probability of making type 1 error? Remember, what do we do with alpha? We make it smaller. How do we reduce the probability of making type 2 error? What do we do with alpha when we want to reduce type 2 error? We make alpha bigger. Very nice. Okay, example 4. A new blood thinning drug is being tested against the current drug in double-blind experiment, and the hypotheses are the null is saying that the average is equal to the old average, and the alternative is saying that the new average is greater than the old average. If the new drug has potentially serious side effects, we should pick a significance level that is, and I have 3 choices of alpha. So let's think of this situation. This is a drug that is good, however, it has serious side effects. So I really want to use it only on those who needs it. I want to avoid the false positive, so I don't use it on those people who don't need it. In this case, to minimize this type, and in this case this would be a type 1 error. To minimize the type 1 error, I would use a small alpha. And in this case, alpha would be 1%. Example 5 is giving you the same situation, but in a different question. It says, if the new drug has no real side effects and costs less than the old drug, we might pick a significance level that is, again, you have 3 choices. Okay, let's look at this situation. This time we don't have serious side effects, so we don't have type 1 error. We don't have to use the small alpha. It costs less, so I really want to use this test. I want to make it so easy to reject the null. And if I want to do that, I should use alpha so big to make rejecting the null easy. And in this case, alpha would be 10%. So up till now, we know that if I want to reduce the probability of type 2 error, I would use a large alpha. Here's another way that you can do to minimize type 2 error. You would use a large sample size. So write this down. To reduce the probability of making type 2 error, we increase the sample size. And let's look at the next two graphs to understand this point. So in this case, you have the null hypothesis proportion equals 0.5, and the alternative is saying that the proportion will be greater than 0.5. This is a right tail test. This is the randomization dot plot, and the sample statistic p hat equals 0.6. Now, when you use a small sample size, you will have a very less diverse situation. So your 0.6 is gonna produce a very large p-value because you really don't have many choices. So a large p-value meaning you're not gonna reject the null. And you know that type 2, you want to make it easier for you to reject the null. So this is not going to help. However, if I increase the sample size, then I will make it easier for me to reject the null. Basically, if I increase the sample size, I will have more diverse values, and it's going to be significantly easier. This way, I would reject the null easier. Sorry. So to reduce type 2 error, one of the methods that we use is we use a larger sample size. So let's look at the effect of sample size. The first thing that you need to remember is that larger sample size makes it easier to reject the null. If you are using small sample size, even the large difference or the effect may not be significant, and this would cause type 2 error to happen more often. With a large sample size, even the very small difference or effect will be significant. So whenever you are using the large sample size, you are minimizing type 2 error. Now, one last note before we end this section. The difference between statistical and practical significance. So let's look at this situation. Suppose a weight loss program recruits 10,000 people for a randomized experiment. A difference in average weight loss of only 0.5 pounds could be found to be statistically significant. So you have 10,000 participants. If each person loses 0.5, this is a huge statistical significance result. However, in real life, if this experiment lasted a year, losing half a pound will really not be practically significant. So there is a difference between statistically significant, even though the numbers are huge, in real life these numbers means nothing. Losing half a pound after 1 year, it really doesn't make any sense. So you really need to distinguish your results. Are they statistically significant or are they practically significant? You really need to check your results and think about the situation before you start accepting it as significant or not, especially when you are using a very large sample size. So in summary, you need to remember that even though using the p-value is great, however, it is not perfect. You will end up making type 1 or type 2 errors, and you can avoid that using the right alpha. So you want to use a correct alpha, and again, it depends on the consequences that you are looking for. Also, another thing that you need to remember, that alpha will be the probability of making type 1 error. And to avoid most of the problems, you really need to do a replication. Basically, repeat the same test, either you or another company, until they produce similar results. Then you would say that your results are significant. The last thing we covered is that whenever you want to minimize the type 2 error, you want to use a larger sample size. And that's it for 4.4. Thank you.